Initial studies have led to a concept designed to provide a reliable, low-cost communication system with maximum capability and in short development time. Major elements are, first, a highly simplified dispensing mechanism capable of carrying 10 satellites per launch. Continuously driven by the Agena secondary propulsion system, the dispenser incorporates a split-hinge device activated by a spring to release the satellites in a spinning mode of 2 revolutions per second. This eliminates the need for conventional spin propulsion equipment aboard the satellite itself. Second, a lightweight satellite powered by solar cells and batteries and capable of either spin or gravity gradient stabilized operation. Primary features are redundant TWT and transponder equipment, a sun aspect ratio designed to provide peak power when needed for battery charge, and a configuration tailored to maximum use of space within the selected nose fairing. The spin-stabilized satellite weighs 65 pounds. For random dispersion in a 5,000 nautical mile orbit, an impulse velocity schedule with a total increment of 200 feet per second has been selected. Orbital injection of all satellites is completed in 33 seconds, and total dispersion within about 4.5 days. At least 4 equally spaced polar planes will be used. Analysis of battery versus non-battery carrying systems reveals a number of trade-offs which will be resolved during the program definition phase. For the Hawaii to Washington link, the battery version, while providing 2 less satellites per launch, has less communications downtime when passing through the Earth's shadow. This shadow condition occurs nightly at about local midnight, but has the most severe effect on communications during fall and winter months. With a smaller number of battery-carrying satellites, the average probability of Hawaii to Washington communications is decreased by 3%, but minimum probability at the winter solstice is increased by 25%. Customer guidance will be required to determine whether reduced downtime is more important than increased average communications probability. Maximum capability, consistent with design simplicity and improved TWT reliability, is assured with the use of batteries. A high-gain version of this satellite would provide increased effective power output and enhanced anti-jam capability without compromising the optimum characteristics of its basic design. Additional subsystems would consist of 4 small solar paddles, a directional horn antenna, and the astronautics vertistat. This is a completely passive orientation device powered exclusively by the gradient of Earth's gravitational field along a primary mylar rod to align the satellite with the local vertical. Shorter secondary rods are used to stabilize the satellite with respect to the plane of orbit and to provide system damping. Because the dispenser design permits complete interchangeability between spin and gravity gradient stabilized satellites, 2 vertistat versions could be tested at low cost and on a non-interference basis in the 2nd and 3rd launches. Gravity gradient stabilization provides an additional 6 to 8 dB of communication system gain. The resulting transponder and TWT effective power output offers one of 2 optional advantages. First, higher data transmission rates can be used in both uncoded and anti-jam modes. Or second, greater signal-to-noise ratio can be developed, which will increase bad weather capability. In addition, a lower gain, wider beam ground antenna could permit more rapid search and acquisition of individual satellites. Although the proposed satellite is not contingent upon the use of vertistat, orbital test is recommended for evaluation of the increased capability offered by this version. The satellite would be produced at Hughes Aircraft's El Segundo plant. Project personnel and development laboratories would occupy 1 floor of the Space Systems Division building, scheduled for completion in April. 15,000 square feet of factory space is reserved for production. This area is completely isolated from adjacent Polaris and Minuteman systems assembly lines. Qualification, performance, and production acceptance testing would be centralized in the Space Environment Simulation Laboratory. This facility is equipped for continuous long-duration tests under a wide range of space conditions. Temperature, pressure, and radiation control covers the spectrum from Earth orbit to planetary flight and landing. Surveyor and SYNCOM experience has resulted in an intimate knowledge of the design, fabrication, and testing of spacecraft structures, auxiliary power systems, telemetry, and communications equipment. Communication systems techniques developed for circuitry and construction of SYNCOM are nearly identical to those for the proposed satellite. Further, the high data rates and range requirements for Surveyor have produced a basic understanding of space communications problems. This is one of 3 portable solar simulators capable of producing a radiation intensity of 150 milliwatts per square centimeter, equaling solar intensity at the Earth's orbit. When mounted on a space chamber, this particular simulator uses 4 carbon arc lamps to project a 5-foot diameter target zone on a specimen. The largest of 4 space chambers stands 50 feet high and provides a test volume of 14 by 15 feet with a vacuum of 1 times 10 to the minus 7th torr. Later this year, a solar simulator with 60 xenon lamps producing an 8-foot diameter target zone will be permanently installed. Here it will be possible to simultaneously subject a number of satellites to long-term environmental conditions. Complementary facilities at Astronautics include this acoustic vibration laboratory with an anechoic and reverberant test chamber. Random noise vibration tests would be conducted here for qualification of individual components, entire satellites, and sections of the dispenser with a satellite installed. Materials, small components, solar cells, and individual parts may be subjected to radiation damage at one of 3 General Dynamics nuclear testing facilities. These include the linear accelerator at Astronautics, capable of bombarding a specimen with 3 million volt particles, the Triga reactor at General Atomic, and the mixed field test pool at Fort Worth, where the effects of protons, electrons, and neutrons are combined. This dual electrodynamic excitation system will be used for vibration tests on the dispenser with all satellites installed. Capable of sinusoidal, random, and mixed sign random excitation, its force output is rated at 15,000 pounds vector for a single operation and 25,000 pounds for dual, with a test frequency range of from 5 to 2,000 cycles per second. This particular specimen weighs 4,800 pounds. A full-scale mock-up of a section of the dispenser, including ejection hardware and a dummy satellite, is being tested under simulated zero-G conditions. High-speed cameras show the satellite as it rotates approximately 45 degrees around the hinge axis. Traveling in a straight line, it continues to rotate around its own spin axis at 2 revolutions per second. Several such tests are underway to demonstrate system reliability. The dispenser will pass through detail fabrication, sub and major assembly in the Atlas factory building. This area will be isolated from all other manufacturing activities. Final assembly, check fitting, satellite mating, and acceptance tests will occur in the environmentally controlled electronics manufacturing facility. All personnel engaged in the project will be consolidated here. The systems and management control techniques applied to this program will be the result of experience gained in projects ranging in scope from Azusa to Atlas. The Azusa transponder, a highly complex electronic communication system, has been successful in 461 out of 465 flights, resulting in a proven reliability of 99.14% as of December 1962. A high percentage of the electronic equipment for Atlas is produced at Astronautics. Other programs, notably Arents, GlowTrack, and Scientific Passenger Pods, represent a depth of experience in both electronics manufacture and systems integration. As prime contractor and systems integrator for the Atlas weapons system, Astronautics delivered 129 operational SAC complexes 3 weeks ahead of schedule set in 1958. The $400 million program, called the world's largest construction job, was completed within 5% of total negotiated costs and involved the management of some 70 subcontractors, 5,000 private concerns, and over 2 million people. Such experience has made it possible to design a communication system based on simplicity, proven technology, and early availability. The proposed concept, while satisfying all program philosophies and requirements, also provides the growth potential so vital to the development of an incrementally operational system.